Yeah. Hello everyone, this is Chakradhar Adupa working as Assistant Professor in Department of EC at SR University, Warangal. Today I am here to discuss with respect to Verilog concepts. I start the topic with introduction to Verilog HDL and I talk about the different types of modeling styles available in Verilog and what are the basic concepts related to Verilog, which usually helps the hardware design engineers to design indicator circuits. So here HDL stands for hardware description language. We do have two different types of HDLs are available. One is VHDL, the other one is Verilog HDL. So today's topic is Verilog HDL. Verilog HDL is a hardware description language used to model a digital system at many levels, ranging from the algorithmic level to the gate level and to the switch level. The complexity of the digital system being modeled could vary from that of a simple gate to a complex electronic digital system, complete system, or anything in between. The digital system can be described hierarchically, and timings can be explicitly modeled within the same description. So here, the Verilog plays a pivotal role in describing the hardware at the industry level. And this hardware description language helps the design engineers to describe the hardware and helps in simulation and synthesis of a hardware. What are the different types of design description available in Verilog? Verilog supports designing at many different levels of abstraction, and three of them are very important. That is behavioral level of description, register transfer level, and gate level. Behavioral level. This level describes a system by concurrent algorithms where each algorithm itself is a sequential. That means it consists of a set of instructions that are executed one after the other, and functional tasks, functions, and always blocks are the main elements which we use in behavioral modeling style. And there is no regard to the structural realization of the design. Yes, when we talk about behavioral modeling style, we do talk about the initial blocks, begin, and always the keywords are going to be used. And we don't bother about how many number of gates are there, instances of the logic gates, because it comes under structural. When we talk about behavioral modeling style, especially in sequential logic circuit designs, we start the blocks called as initial block and always block, and begin and end keywords are going to be used in the behavioral modeling style. We come to each of these modeling style with examples in coming classes. So behavioral modeling style at this stage, I can say that it describes a system by concurrent algorithms, and each algorithm itself is a functional and sequential, and it consisting of set of instructions for executing each. Next is register transfer level. Register transfer level designs using the register transfer level specify the characteristics of a circuit by operations and transfer of data between the registers. An explicit clock is used here. RTL design contains exact timing, bounds, operations are scheduled to occur at certain times. Modern RTL code definition is any code that is synthesizable, which is called as RTL code. Next is gate level. Within the logic level, the characteristics of systems are described by logical links and their timing properties. All signals are discrete signals, and they can only have different logic values as 0 or 1 or don't care X or high impedance state Z. The four possibility values are either maybe 0, X or 1 or Z. The usable operations are predefined logic primitives, so called as AND or NOT. And using the gate level modeling, it might be a good idea for any logical level of the design, but it will become a cumbersome and laborious work when we go for larger designs. The gate level code is generated by a tool like synthesis tools, and this netlist is used for gate level simulation and for backend. In Verilog HDL, what is simulation, what is synthesis? Once a design block is completed, it must be tested. The functionality of the design block can be tested applying stimulus and checking results. We call such a block the stimulus block, where we provide the all possible combinations of inputs such that we're able to test the output for each and every corresponding input combination. So these set of input combinations so called as stimulus. Keep the stimulus and design block separates. The stimulus block can be written in Verilog. A separate language is not required to describe stimulus. The stimulus block is also commonly called as a test bench. Different test benches can be used to thoroughly test the design block. Two styles of stimulus applications are possible. In the first style, the stimulus block instantiates the design block and directly drives the signals in the design block. The second style of applying stimulus is to instantiate the block, the stimulus and design blocks in a top-level dummy module. The stimulus block interacts with the design block only through the interface, and the function of top-level block is simply to instantiate the design and stimulus blocks. What is functional verification in Verilog? For functional verification in Verilog, the process typically involves writing a test bench to simulate the functionality of the module using Verilog design. And here, some of the mentioned steps are followed. Key steps and examples you can use to verify the function, considering a 2x1 multiplexer. So I start with the steps here. The steps of functional verification is designing a function. This is your Verilog module, which contains the logic you want to verify. And write a test bench. A test bench is separate Verilog file that applies to stimulus to your design and checks the output. Simulate, where we simulate Verilog simulate code using a simulator called as Model Sim, Icarus, Verilog, or Vivado, or it might be any kind of simulator which supports HDL to run on your test bench. And to verify the functionality of the output, checking the output, compare the expected output with the actual output. For example, if I consider 2x1 multiplexer here, the 2x1 multiplexer, sorry, considering example of Verilog model of 2 by 1, 2x1, 2:1 multiplexer that selects between A and B based on selection line signal. And we write a test bench for the 2x1 multiplexer considering all possible inputs of selection line 0 and selection line 1, what happens. So when you simulate and verify, we use the Verilog simulator to compile and simulate the test bench. The $monitor statement will display the values of A and B and selection lines and Y during the simulation. And you can observe the output Y behaves expected for each combination of the inputs. And the expected output will be Y, and that will be decided based upon selection line. Yes, if S is 0, I0 will be passed on to the Y, and if is 1, selection line is 1, then Y will be equal to I1. That is example we consider here is selection line 0, the output Y equal to A, the selection line Y should be equal to B. And this is a basic example. You can expand this idea to more complex designs by writing step benches that cover corner cases and edge conditions for the function you want to rectify. Would you like to proceed with Verilog specifying Verilog design? So you have Verilog code ready, then we can share any Taylor test bench. That means anyone is comfortable with the Verilog coding, they can easily write the test bench because the test bench actually involves the set of possible inputs, and based on that, the design is going to simulate and check the functionality of the design with corresponding outputs with respect to the stimulus. System tasks and functions. Verilog provides standard system tasks for certain routine operations. All system tasks will appear in the form with the dollar. Operations such as displaying on screen, monitoring values of nets, stopping, and finishing are done by system tasks. Next is Program Language Interface, usually called as PLI. PLI provides an active interface to a compiled Verilog module. The interface adds a new dimension to working with Verilog routines from a C platform. One can read data from a file and pass it to a Verilog module as input. Delay values, logic values, etc. within a module can be accessed and altered. Module. In a Verilog module, the very first keyword people use to understand is a module. What is a Verilog? Verilog provides a concept of a module. A module is a basic building block in Verilog. Module can be an element or a collection of lower level design blocks. Elements are grouped into modules to provide common functionality that is used at many places in the design. A module provides the necessary functionality to the higher level block through its port interface, inputs and outputs, but it hides the internal implementation. This allows the designer to modify module internals without affecting the rest of the design. A module can be defined at 4 levels of abstraction depending on the needs of the design. The module behaves identically with the external environment irrespective of the level of abstraction at which the module is described. The internals of the modules are hidden from the environment. When we go for a behavioral model or algorithmic level, this is the highest level of abstraction provided by Verilog HDL. A module can be implemented in terms of the desired design algorithm without concern for the hardware description, implementation details. Designing at this level is very similar to the C programming. Data flow level. At this level, the model is designed by specifying the data flow. The designer is aware of how data flows between the hardware registers and how the data is processed in the design. Next is gate level. The module is implemented in terms of logic gates and how much hardware is used in terms of the module and how the interconnections are going to establish between the gates. And the designing at this level is similar to describing a design in terms of a gate level logic diagram. Next is switch level. This is the lowest level of abstraction provided by Verilog. A module can be implemented in terms of switches, storage nodes, and the interconnection between them. Design at this level requires knowledge of switch level implementation details. Simulation and synthesis tools. Simulation and synthesis are two fundamental processes in Verilog design and development, each serving a distinct purpose in digital circuit design. One is simulation. When we go for simulation Verilog is a process of testing and verifying the behavior of a digital circuit described in Verilog before it is synthesized into hardware. It helps check the functionality of the code by running it through a simulator, where you can apply test inputs and observe the outputs over time. What are the steps are involved for simulation? Write a Verilog code, create a test bench, and go for simulation and analyze the output. So the writing a Verilog code is so-called the design under test DUT, and creating a test bench provides plausible stimuli to the DUT and checks the responses. And the design is using a Verilog simulator like Model Sim or Icarus, Verilog, Vivado, or Cluster Sim. So it supports the Verilog hardware description language. You can use any kind of simulator. But when it comes to the analyzing the output, using the waveforms or logs on to ensure the design behaves as expected. Here comes the concept of synthesis. Synthesis in Verilog is a process of converting the Verilog code into a netlist that describes the actual hardware circuit using logic gates, and the synthesizer design can then be implemented on an FPGA or ASIC based on the need. The basic steps involved in the synthesis is writing a synthesizable Verilog code to ensure that the code is written in a synthesizable form. Constructs such as initial blocks, outside test benches, or delays are not synthesizable and should be avoided. Using a synthesis tool like a Xilinx Vivado, Synopsys Design Compiler, or Intel Quartas are used to perform synthesis. Generating a netlist is the process where a tool generates a netlist, a gate level representation of your design. An implementation of FPGA and or ASIC, the netlist can be mapped onto a specific hardware, either on FPGA or an ASIC fabrication based on the need. Using the constructs such as always at the rate of passage of the clock, a sensitive construction in Verilog, or flip-flops and combination logic circuits in assignment statements, or always at the rate of asterisk star blocks avoids initial hash delay or dollar monitor statements as they are not synthesizable. When it comes to the keywords and identifiers in the Verilog, keywords are the special identifier reserved to define the language constructs. Keywords are in the lowercase always. Identifiers are the names which are given to the object so that they can be referenced in the design. Identifiers are made up of alphanumeric characters, the underscore, or the dollar sign. Identifiers are all case sensitive. Identifiers are case sensitive because Verilog supports case sensitive. Identifier starts with an alphanumeric alphabetic character or an underscore, and it should not start with a number. They cannot start with a digital number or a dollar symbol, or the first character is reserved for system tasks, so which are explained later in the talk. Reg value. Reg is a keyword. Value is an identifier. And input clock. Input is a keyword. Here, CLK is an identifier. Here, value is an identifier. Reg value means value is an identifier. Reg means it's a keyword. Input CLK. Input is a keyword and CLK is an identifier. The double slash in this particular statement indicates that it's a comment. So by writing a double slash beside the instruction in the Verilog, we can mention any keyword or any comment related to the instruction or the meaning of the key statements. Next is white space characters. The white space or the blank spaces, tabs, and new lines comprises also called as together white space characters. The white space characters usually we use in Verilog is \P for mentioning the blank space, \T for tab, and \N for new line, and so on. White space is ignored by Verilog except when it separates tokens. White space is not ignored in strings. Comments. Comments can be inserted in the code for readability and documentation. There are two ways to write comments. That is, a one-line comment starts with double slash, Verilog skips from that particular point to end of the line. A multiple line comment starts with slash asterisk star and ends with asterisk star followed by slash. A multiple line comments cannot be nested. One line comments can be embedded in a multiple line comments. For example, A is equals to B double ampersand C. This is a one line comment double slash. That means I can able to make a meaning of this particular instruction that A is implied with the AND operation of B and C. And here the next statement, if you see slash followed by asterisk star, this is a multiple line. Multiple line comment is going to start with slash followed by asterisk star. And you look at the third next line, comment asterisk star slash. And the next line, slash asterisk star, this is a followed by slash asterisk star. It's an illegal comment because multiple slash stars are involved in this particular line. We cannot mention that it as a comment. So if you comment a last line slash asterisk star, this is a valid legal comment and it is ended by asterisk star slash. That means the above line mentioning multiple times slash asterisk star, we cannot use multiple times. Only at the starting of the comment, we can, if it is a multiple comment line, once you use a slash star at the starting of the line, and at the last, you can stop or close it the comment by asterisk star followed by slash. But we cannot use in between. Number specifications. There are two types of number specifications in Verilog, sized and unsized. This actually is used for the representation of a different type of numbers. What we mentioned might be a binary number, or hexadecimal, or decimal. So here comes the usage of this particular keyword called sized or unsized numbers. Sized numbers are represented as mentioned by size before the base format and before the number. For example, the size written in the braces only in a decimal and specifies the number of bits in that particular number. The legal base formats are D for decimal, H for hexadecimal, B for binary, and O for octal. The number is specified in the consecutive digit from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, F actually for hexadecimal number. Only a subset of these digits is legal for a particular base called as H. The uppercase letters are legal for number specifications. For example, a 4-tick B1111 indicates that it's a 4-bit binary number. Here, 4-tick means it's a 4-bit number, and B means it's a format of the particular number. B means it's for binary, and 1111 it's a 4-digit binary number. Second one, if you observe 12-tick HABC, this indicates that 12-tick indicates that it's a 12-digit number, and H stands for it's a hexadecimal, whereas the number is ABC, and each of represented with 4 bits, that is 12. ABC is a hexadecimal number. And the last one is 16-tick D255. It's a decimal number of 16 digit, that is a 255. And you can see the comment, this is a 16-bit decimal number. When it comes to the unsized numbers, the numbers that are specified without a specification are decimal numbers by default. Because when we mention, I will come back to the previous slide. Look at here, there is an example of 4-tick B, 1111, 12-tick H, ABC, 16-tick D, 255. It indicates that we are mentioning here the format of the particular number is a binary number, hexadecimal, and decimal. If at all, if you're not mentioning any kind of the number formatting in the unsized numbers, we can consider that as a decimal number by default. The numbers that are written without a specification have a default number of bits that is simulator and machine specific must be at least 32. So here, there is no bit format here, 2, 3, 4, 5, 6. Straight away, it is considered as a 32-bit decimal number by default. And here, HC3, the 32-bit hex digit number. O21, it's a 32-bit octal number. We are not mentioning any kind of the size here. So default, it will take the machine will take it as 32-bit unsized number. There is a special case of representation of numbers. One is the X or the Z. Verilog has two symbols for unknown and high impedance values. These values are very important for modeling real circuits. An unknown value is denoted by an X. A high impedance value is denoted by Z. 12-tick H13X. This is a 12-bit hex number where 4 least significant bits are unknowns. And a 6-tick HX. This is a 6-digit 6-bit hex number. 32-bit BZ. This is a 32-bit high impedance number. X means unknown or don't care. Z means high impedance state. Next, negative representation of negative numbers. The negative numbers can be specified by putting a minus sign before the size of a constant number. A size constants are always positive, and it is illegal to have a minus sign between the base format and number. So we cannot use a minus symbol in between the base format and number. You need to mention it in the very first itself. An optional sign specific square can be added for signed arithmetic. For example, minus 6 tick D3. It's a 8-bit negative number stored as a 2's complement of 3. Second example, minus 6 tick yes D3. It's used for performing a signed integer math. 4 tick D minus 2. It's an illegal specification. You cannot mention the minus symbol in between the base format and a number is already mentioned here. Next is underscore character and question marks. Underscore characters are always allowed anywhere in a number except the first character. You cannot make it in the very first character. Underscore characters are allowed only to improve the readability of the numbers and are ignored by Verilog. A question mark indicates in Verilog Hdl as an alternative to for its Z in the context of numbers. Especially, this can also be used as a ternary operator in when you are writing a case statements and for if statements for writing using a ternary operator. And this question mark is used to enhance readability in the case X and case Z operations also. For example, 12 tick B 1111 underscore 0000 underscore 1010. Here it is a 12-bit binary number. Complete starts from 4 ones to 4 zeros and finally 1010. So for readability purpose, if you are mentioning the underscore between the 4 digits and again next 4 digits and so on, it helps to the reader to analyze and read the 4 bits. 4 tick B10 question mark question mark. It's equivalent to a 4 tick B10ZZ. Next is strings. A string is a sequence of characters that are enclosed by a double quotes. The restriction on a string is that it must be contained on a single line, that is, without a carriage written. It cannot be on a multiple lines. Strings are treated as a sequence of 1 byte ASCII values. For example, if you see this first one, started with double quotes, in between the double quotes, it's a string. Whatever we write in the double quotes, it can be considered as a string. So there's a first example is hello Verilog world. It's a string. And you can look at here, second line, the last example, A/B, two are written in double quotes. It's considered as a string. Value set. Verilog supports 4 values, that is 0, that is logic 0, false condition, 1, logic 1 is a true condition, X is unknown logic value, don't care, and Z is a high impedance state or floating state. Verilog supports 4 values and 8 strengths to model the functionality of the real hardware. So these are the basic 4 values 0, 1, and X and Z. And strength levels are supply strong strength level, strong, pull, large, weak, medium, small, and high. And the types of driving type or storage type or high impedance. So the strength level starts from weakest one is a high impedance state and the strongest driving is a driving type strength level. These are all possibilities of 8 strength levels in the available in the Verilog. Verilog data types. Verilog Hdl has 2 groups of data types. One is net data type, another one is variable data type. Net data type. A net data type represents a physical connection between structural elements. Its value is determined from the value of its driver, such as a continuous assignment or a gate output. If no driver is connected to a net, it goes to a default high impedance state, so called as Z. So this what we can say in terms of net data type. And the another one is variable data type. A variable data type represents an abstract data storage element. It is assigned values only within an always statement or an initial statement, and its value is saved from one assignment to the next. A variable type has a default value of X. Next comes about scalars and vectors. Nets or reg data types can be declared as vectors with multiple bit widths. If the bit width is not specified, the default is a scalar because it only carries one value. When you want to have multiple values which is going to be carried, we preferably use called as vectors representation. Vectors can be declared as a high is to low. That means whether it is low is to high or high is to low, based on the bus width we mentioned, the starting and ending values. But the left number in the square brackets is always the most significant bit preferably. Example, wire A, it's a scalar because it carries only one bit, one digit of information. A scalar indicates with a single variable. But when I want to represent it as a bus, so you can say here the second line wire 7 is to 0 in the square brackets. It indicates that 7 is the maximum most significant bit and 0 is the least significant bit. That indicates from 0 to 7 this wire bus name is going to carry 8 digits of information. And another one, if you observe, wire 31 is to 0. So here indicating a bus A, comma bus B, comma bus C. Here is combined declared that is a bus A, bus B, bus 3, bus C, sorry. All three bus A, B, C's are 32-bit width and carries some MSB as 31, that is MSB is 31 is to 0. It indicates that bus A is capable of carrying 32 bits of width information and bus C is also carries 32 bit of information. So this way, we can also declare the buses in a combined fashion with wire 31 is to 0, bus A, comma, bus B, comma, bus C at a time. Individually also we can declare, combinedly also we can declare like this. And next is reg clock. So reg clock is a scalar quantity and it's a mentioned as a register. Reg 0 is to 40. It's actually a virtual address is mentioning starts from 0 and the maximum address is 40. So with this vector register value address starts 41 bits wide. Next is parameter. Verilog allows constants to be defined in a module by the keyword called as parameter, especially whenever it comes to talk about a constant, we use a keyword called as parameter. A module by the keyword called as parameter cannot be used as a variable because it helps only to define or declare a constant, not the variables. A parameter values for each module instance can be overridden individually at compile time, and this allows the module instances to be customized. Parameter types and sizes can also be defined. Parameter port ID is 5, as defined as a constant. Parameter cache line width is 256. Parameter signed is 15 is to 0 is the width. The fixed width of 16-digit width. Range starts from 15 to 0. These are the examples of definition of parameters. Next concept we talk about operators. There are different kind of operators are available in Verilog. What are all these things? We'll see now. Operators are the three types: unary operators, binary operators, and ternary operators. Unary operators preceded the operand, and binary operators appear between the operands, and ternary operators have two separate operators that separate three operands. If you look at the example, minus A is equals to negation of tilde B. So the tilde is a unity operator here, where the B is the operand. That implies that the complement of B is assigned to A. So minus A is equals to B ampersand ampersand C. The next line, where double ampersand is a binary operator which indicates the operation between the B and C operators as an AND operation. In the third example, minus A is equals to B question mark C is to D indicates that question mark is a ternary operator and B, C, and D are the operands. So we stop here for today's class, and we'll stop here, and the next talk will be continued after the operators in the next video. Thank you all for supporting me, and thank you everyone for patiently listening this particular video. If you don't like this video, please mention the comments on the comment box. And for any suggestions, you can please mention your comments in the video. Thank you one and all. And the next slide will be continued after the break.